Hello. So today's session is related to feedback networks as well. We had a few questions from the past week. We will first discuss those questions and then we will continue our week 12, that is the last session. And that's also related to feedback networks. Let's wait for 5 minutes, then we will start. I guess can start. Okay, so these are a few numerical questions related to past week, week 11, which was based on uh, feedback networks. So we can start. Let's have a look at this question. What does it say? Okay. The values of the components are given, R in and R out, and the gain is also given to us as equivalent to 175, and feedback network gain is zero point 0.1. The values of the components in the ideal case are to be treated as R infinity, R in B as infinity, such that whole potential drops here, and R out B is 0, such that there is no loading effect due to this resistor. And in case of non-ideal case, R in B is 500 ohm and R out B is 1.5 kilo ohm. Consider the load resistor to be 4K. So what is the first question? We have to find the overall voltage gain, that is ABF V0 by Vs. Vs is here, V0 is here. V0 by Vs for an ideal feedback network. Ideal feedback network means we have to treat R in B is equivalent to infinity and R out B equivalent to 0. The values, okay, how can we do this question? By following simple steps. Just look here. Okay, at input Vs is B in plus Vf, right? Because R out B is equivalent to 0, so my Vs is from this node to this node, that is equivalent to Vn plus Vf. From feedback network, Vf is equivalent to beta Vx, right? And if we see Vx nodes are from this node to this node, that is V out. So Vx is your V out. So this implies Vf is equivalent to beta times V out. This implies Vs is equivalent to V in plus beta times V out. Alright. Now if you see this loop now, what is the voltage? Voltage is given to us as AVV in. It will drop across R out and R load, right? Therefore V out is voltage across RL, so V out is AV V in into RL divided by RL plus R out. We can call this AV RL divided by RL plus R out as AV dash, right? If R out is 0, that is for the ideal voltage amplifier, then AV dash will be equivalent to AV. So my Vs will be equivalent to V in plus beta times V0, and V0 is AV V in RL divided by RL plus R out. That means it is V in 1 plus beta AV dash. So my Vs is equal to V in 1 plus beta AV dash, right? So my V0 by Vs, so V0 in terms of Vs, we got it V0 as AV dash V in. So my V out is AV dash V in will be Vs divided by 1 plus beta times AV dash. So my V0 by Vs will be AV dash divided by 1 plus beta times AB dash. Wait a second. Yes, correct. So my AB dash, can call it as AB RL divided by RL plus R out whole divided by 1 plus beta times AB RL divided by RL plus R out. We substitute the values. Let's first find what is RL divided by RL plus R out. RL is 4K and R out is 1K. 4K divided by 1K, that is 4 by 5, and AV is given to us as 175. So we know the VS will be 175 into 4 by 5, 1 plus beta. Beta is 0.1. 0.1 into 175 into 4 by 5. If you go on solving this, you will find V naught by Vs as 9.33. Okay, so this is how you do the questions with the feedback networks. Voltage gain is reduced by this factor 1 plus A times B. Now moving on to the another part, that is to find the input resistance due to an ideal feedback network. Again, looking back at the circuit, I had to find this resistance, right? If there was no feedback, it would have been simple. Rn, now it is feedback, so we have to calculate, we're taking into feedback network into account as well. So starting from again KVL at input, Vs will be equivalent to Vin plus Vf. Again Vs will be equivalent to Vin plus beta times V naught, and this will be equivalent to AB RL divided by RL plus R out into Vin. So it will be Vin will be Is times Rn. Second. So it is Is times Rn plus beta times AB RL divided by RL plus R out into Is times Rn. My Rn dash, that is the total input resistance, will be given by Vs by Is. So my Vs by Is will be Rn plus beta times AB dash, where AB dash is this. We calculated it in previous step as well. So it comes out to be Rn 1 plus beta is 0.1 and AB dash is equivalent to 140, and it will be equivalent to Rn is 2k plus into 15, and that will be 30k. Okay, so it will be 30. Okay, now output resistance. Output resistance we will calculate by using the test source V out and by give me R out. If we look at the circuit, we will use the circuit here to find R out, then we will calculate it in parallel to RL. Okay, so let's start. At this time, Vx is 0, so this implies Vin plus Vf will be equivalent to 0, right? This implies Vin will be equivalent to minus Vf, and Vin will be equal to minus times beta V naught. Now if we look at the output, V output will be equivalent to I out if we consider here a current of I out times R out plus AV V in. So my V out will be equivalent to I out R out minus AV beta times V out. So my V out times 1 plus 8 V times beta is R out. This implies R out dash will be equivalent to R out divided by 1 plus AV times beta. So it will be equal to R out is given to us as 1k divided by 1 plus AV 175 into 0.1, that is 1k by 18.5. So now total R out dash, that is double dash, will be equivalent to R out dash parallel to, we calculated this resistance and it will be in parallel to RL, right? And RL is 4 kilo ohm. First let's see, R out dash is 1000 divided by 18.5, that is 54, approximately 54. So it will be 54 into RL is 4k divided by 4k plus 54, that is 54 into 4 to 16k divided by, it will be 4.045k. It will be equivalent to 53.2 ohm. Okay, so this is how you calculate R out. So it will be 53.2. Now we have non-ideal feedback network. That is your Rn beta is equivalent to 500 ohm and your output beta is equivalent to 1.5 kilo, right? Due to these factors, your gain will change from AV dash to AV double dash, and your beta will also change to beta dash. Let's see. You know that from the feedback network, we just look here. It's here, your feedback network. If it is R out B, and now consider this as an amplifier, your beta is gain, right? And your load resistance will be R in. So your beta dash will be equivalent to R in divided by R in plus R out, right? And your beta dash using the values will be R in is, sorry, it is beta times R in, 0.1, 0.1 into R in is 2K divided by R in 2K plus R out is 1.5K. This is R out B, sorry, this one, R out B is 1.5K. So your beta dash, if you do the calculation, comes out to be 2 by 35. This is your beta dash, right? So this is beta dash 2 by 35. And your AV dash will change because your load resistance will come in parallel with R and B, so your RL will be RL dash, that is given by RL parallel R input beta, right? So that will be 4K into 500 divided by 4K plus 500, and this will be equivalent to 2000K divided by 4.5K. So your RL dash will be equivalent to 4, right? Now your AV dash will be equivalent to AV RL dash divided by RL dash plus R out. AV is given to us as 175, and this will be calculated, sorry, plus 1K. Okay, so let's just calculate it. 175 multiplied by 4.4 by comes out to be 53.84. So this is your new gain. It has changed because of the loading effect of the another resistor. So my Rn dash, we can just directly calculate it as Rn dash plus 1 plus beta dash AB dash. So this is 2k plus 1.5k, because now you have another resistor in series. So if you take the whole feedback network into account, and then you have to change the input resistance as well. So it will be 1 plus 2 by 35 into 53.84. So R in dash double dash will be equivalent to 3.5k 1 plus 53.84 divided by 35 plus 1, that is 0.0 into 3.5k, comes out to be 14.268. This is your new input resistance. Now in this question we have to calculate output resistance. These are the values for the non-ideal feedback network, and we have to consider the load resistor as a part of voltage amplifier, right? Okay, let's go back to circuit first. We have to calculate this R out, right? Here, this one. And now we have feedback network as well with non-ideal values R for R and B, and it is in parallel with RL. Okay, we will calculate from this point, then we will treat it in parallel to RL and RNB. Inches. Okay, so for this circuit we have to find output resistance, including the non-ideal values of R and B as well. So now if we look at here, if we apply a test source V out I out, and the current of I out flows through here, so what we can write it as V out here is equivalent to I out into R out, simple KVL, right, plus AV V in is given here. Simple calculations, I out R out plus AV. So what is V in here? We know that when we have to calculate output resistance, you short the input values. You use the 0 here, right? So basically, your if your Vs is 0, and if you apply the KVL from this node to this node, Vs is Vin plus Vf, right? And it will be, hello. Do you have any doubts or questions? You can unmute yourself and then ask. So it will be 0. So your V in will be simply equivalent to mu s. You don't need to say sorry. You can just have conversation with me. Okay, so my V naught will be, so here it's minus beta times, since Vn is Vf, let me just first write in this step a simple Vf minus times Vf. So my I out, R out, minus AB Vf. Now if we look here, Vf is beta Vx, right? And your Vx is V out. So Vf is beta times. See here, Vx is from this node to this node. If you translate to this, it will be from this node to this node, that is V naught. So your Vx is V naught. Okay. So total V naught will be I out, R out, minus AB. I'm using beta dash because we have seen that beta value changes when you use the non-ideal values of the feedback network. So it will be beta dash, not beta, plus taking the V naught common, beta dash to be, now my output resistance, that is R out dash, will be simply V naught by I naught. That will be equivalent to, we have to transpose it here, 1 plus AV beta dash, right? Your I out is, R out is given to us as 1K, 1 plus AV for open loop gain is 175 into beta dash we have calculated, it is equivalent to by 35. Let me just calculate it. 175 to divided by 35, that is 10. It comes out to be 1K by 11, and thus your dash is equivalent to 90.9. Okay, now again, since we have to find output resistance, taking into RL into account as well. So your RL, can you tell me what will be the condition for RL and RNB? Are they in series or are they in parallel? Can you look at the circuit? RNB and RL. No, just look again. See the nodes. We know when are the two resistors parallel and when are they in series. These are three nodes. If I apply a voltage here, they have one common node and another nodes are different, so they will be in series. When resistors have both nodes common, this and this node is common, right? AB is common, this is C and D. C and D are common. Common means same nodes, they are in parallel. So here if you look here, R and B has this node, let's call it A, and RL has node, let's call it B. This will be A here, and R and B's second node, let's call it C, and RL's node, let's call it D. So can you see here, A and B are at same position, and C and D are also connected. So if they have both nodes same, then they will be in parallel, right? So these, right? So these resistors will be in parallel. So you have to first calculate RL. You calculated this R out by using this formulation, that is 90.9 you got. Now you have to find RL dash. That will be RL parallel to RN B, right? Here RL parallel to RN B. I have calculated in previous step. Let me just go back there. Here RL parallel RNB, it will be 4K parallel 500 divided by 4K plus 500. It comes out to be 444.4. We'll just write values here. 0.4. Now your total R out. Now we have combined value for your load resistance and you have R out, and these two are also in parallel, right? So your total R out dash will be R out dash parallel RL dash. So that will be 90.9 into 4 divided by 90.9 plus 4. Solve this, you will get an answer of 75.46 ohm. Okay, so let me just show you. We calculated for the transistor here, we calculated this R out, right? We calculated an R out for this black box. Now you have connected resistor RL dash. So your R out, this calculated R out dash, and this RL dash are in parallel. So that's how we calculated R double dash. Okay. Now I will ask you this, if you can answer me this, that will be good enough. Have you studied the different topologies? Voltage shunt, voltage series, series shunt, and shunt. Okay, so can you, so this is a circuit, right? So in the circuit you have all these values given. We will just go through the first question. Identify the feedback topology in the amplifier. Can you tell me which type of topology is it? Give it time. You don't have to make haste. You can look at the circuit and answer me this. See here. First, identify which resistor. Here, I will just give you a hint. Here, one resistor is applying as a feedback. So you can identify the resistor first, then understand which type of feedback topology is it. Are you able to understand it? Okay, series means you are taking a sample current at the output, right? And look again, what are you applying at the input? You said series voltage, right? So it will be, yes, right. So it will be current at the output and voltage at the input. Okay, so it will be current series. Is the D correct option? Okay, nice. So this was the first one. Okay, next part. We have to find a value for RE1 such that we have to find the range of this. Have you gone through videos? You must have seen the videos. I will also give you a summary of it, and let's just solve this question together. First, we need to find your current R0, R pi, GM, etc. Right? So let's just start. First, just copy this. Go. Sorry. We will follow from this step. We'll use a KVL from this node to this node. So what will be? It will be VCC equivalent to, if a current IB flows through here and from this node to this node, what is the voltage? VBE, right? And that is given to us as 0.6. Beta is also given, VA is also given. We will use these values after that. And current of IE flows through this, because this is a, what type of first let me know what is the type of transistor it is. Is it a NPN or PNP transistor? Can you identify it? Right, NPN. Okay, so this is emitter, right? So this is a current of IE here flowing, IB is here. We can apply the KVL now. VCC will be IB RB plus VBE, voltage drop across body, base and emitter terminal, plus IE, and IE flows through combination of RE1 and RE2, right? So my VCC will be IB RB VBE. So can you tell me what is IE? What is the definition of IE? What is it equal to? I is the emitter current, right? So it is equivalent to, in terms of base, no, not exactly beta times IB. You can approximate it, but it's not equal to beta times IB. Can you tell me the exact definition? IC is beta times IB. What is IE? You have transistor here, you have IE here, you have IB here, you have IC here. So what will be your IE? This is IE, this is IB. One second, let me draw it neatly. So this is your transistor BJT, right? If I consider this as a node, so your IE current is injected and IB and IC flows in this way. So what will be IE now? Apply KCL at this node. Can you tell me what will be IE? Yes, right? So it will be IC plus IB. Now apply IC equal to beta times IB. That is the correct definition, right? So that will be beta times IB plus IB. So your IB can be written as, if I take now IB common, it will be beta plus 1 IB. That is the exact definition. You can approximate it with beta times IB because beta is usually high, but exactly if you want to write exactly, then it is beta plus 1. So this is beta plus 1 IB RE1 plus RE2. Okay, so IB RB can be written as, sorry, plus beta plus 1 IB RE1 plus RE2 will be VCC minus VBE, and we have to find IB, so it will be plus beta plus 1 RE1 plus RE2 VCC minus VBE. So IB will be equivalent to VCC minus VBE divided by RB plus beta plus 1 RE1 plus RE2. Okay, so from the definition of IC now, IC is beta times IB. So it will be beta times IB is VCC minus VBE divided by RB plus beta plus 1 RE1 plus RE2. Okay, so now let's see what are the values given to us. Beta, what is the beta? Beta is 200. Okay, we need beta, we need VBE on, that is 0.6, VCC 12, so it will be beta is 200, this is 12 minus VBE on is 0.6 divided by RB, RE1 and RE2. RB is 1.55 mega, RE1 is 380, RE2 is 620. 1.55 mega plus beta plus 1, that is 201, RE1 plus RE2, that is 380 plus 620. Okay, so IC will be, let me just calculate a bit, 12 minus 0.6 into 200, that is 2280 divided by 1.55 mega plus 1, that is plus second 0.2 mega. Just 1 second, 201, 0.2 mega, that will be 2280 divided by 1.75 mega. Let me just see what is the value. 2286 divided by 1.75 comes up to be 1306 divided by mega, that will be 10 is 6. So my IC can be written as 1.306 milliampere. We can write it as 1.3 milliampere. So this is your IC. Okay, so you have written something. Okay. Now, do you know the definition of GM, R pi, and R naught? How you calculate GM of the BGT? We have seen those definitions in the first session. So GM is calculated by using this formula, IC by VT. Yes, right. And it will be then 1.3 milli and Vt is thermal equivalent voltage, that is 26 milli. It will be 0.3 divided by 26.05, right? And R pi is beta by Gm, right? Beta is now 200 and Gm is 0.05. So my R pi is 200 into 100 divided by 5, that is equivalent to 4 kilo ohm. And also we have to calculate R naught. What is the R naught? How does R naught appear in the circuit? R naught R naught is because of the early effect, right? Early voltage. If you have early effect in the transistor, right? VA by IC. And do you know what is early voltage? What does early voltage signify? If early voltage is very low, what does it say? Early voltage is 130. IC is 1.3 milli, so it is 100 kilo ohm. So what does early voltage signify? If early voltage is less, so what will be the transistor behavior? So let me just draw IT. Sorry, not IT. IC VC. Correct me if I'm wrong. So this is your early voltage, right? Is this correct? This is your simple ICVC behavior for the BJT. Can you see it? Can you see it, or you want me to explain it if you don't know? Can tell me, I will just explain it. Do you want me to explain what is early voltage? Okay, let me just explain it. So when you have the transistor, this is your ICVC behavior, normal behavior, right? So you go on increasing your VCC, your current will increase, then it saturates, right? So this is normal BJT behavior. It's saturated. It's ideal behavior. This is the ideal behavior. Ideal behavior means that if you go on increasing VSVC after saturation voltage, VSAT, let's call it VSAT, your current does not increase further. Okay, so if it increases further, we signify it. Sorry, we what does it say? We come to know about it by using the value of VA. If VA is large, what does VA is? We use the tangents here. Use the tangents on the surface. If I use a tangent on the surface and on the x-axis, if this tangent cuts the x-axis at any point, it's called as a early voltage. So if it has an ideal behavior, so it will run parallel to your x axis, right? So VA will be infinite for ideal BJT. So but in real case, with VCE your current also increases. Let's say after saturation it increases in this way. So if I draw the tangents here, so it cuts this axis at this point. So this is your early voltage. If early voltage is now, how can we know about the transistor behavior using the early voltage? If early voltage is very low, that will signify that your BJT, after achieving a saturation, still your current will increase with applied collector voltage. In ideal case, with applied collector voltage it will remain constant after saturation, but in this case it will increase. So if VA is less, so after saturation your current will further increase due to VC. Okay, so this is how VA is applied in the BJTs. Okay, now we have calculated all the values. So what do we need to do further? Wait a second. Okay, now we have to see what is the value of, what is the range for, one second, range of RE1. We have to calculate range of RE1. Did you understood this earlier voltage? What is it and how do we analyze the transistor behavior using early voltage? Okay. Now for the transistor, in the feedback, we have few conditions, right? First, you gave the right answer when you said that it is in current series. So your feedback element is RE1, right? And if it is current series, then that means your feedback voltage is Vf and your current was IE and it was IE1. So Vf by IE is RE1, right? So can I say that for feedback it is beta times IE, right? So your beta is simply RE1, correct? So for this transistor your beta is RE1. Your beta is RE1, correct? And your intrinsic transistor GMA is simply GM, right? That is the transistor gain. If we make the small signal analysis, this is GM, right? GM VBE. So A is GM. And further, mm, next is your R naught. Your R naught, if you see your, let me just draw first the equivalent circuit for this transistor. Do you know how to draw the equivalent circuit? Okay, I will draw. If you know, you can correct me if I'm wrong, right? So you short the capacitors. Right? This is your equivalent circuit. Is this correct? Okay, fine. So we can move on. Now you know your intrinsic resistance, for the transistor to have a gain, your intrinsic resistance, so okay, this should be greater than RC plus either RC, either it should be greater than RC individually and RE1. Sorry, this is RE1, right? And if you go on calculating this GM dash due to the, if you consider the RL as well, let's just ignore that fact, loading effect. We will just use the GM only. And now, do you know how to calculate input resistances? You have gone through the videos, right? You apply the test source, then you use VTest by ITest as R input. I will just directly write the value for Rn. Rn will be equivalent to R pi, and similarly R out here. If I apply R out here, so it will be R naught. Now for the feedback network. For the feedback network, what are the conditions? You have gone through the videos, right? So your R out beta, that is a feedback, should be less than equal to Rn, and your Rn for the feedback network should be less than R out. Also loop gain, that is beta feedback, should be greater than 1. Now if you look at here, your R in, this is your R out beta, this is your R in beta, both are equivalent to RE1. So that means RE1 should be less than equal to R pi, that is your Rn, and RE1 should be less than equal to R naught, that is R out. When you go through the lectures, you will understand these things correctly, because these are the basic transistor properties and ideal, such that the device behaves near about ideally. These are the few conditions. And also A dash beta feedback should be greater than 1. And since we calculated as GM times beta should be greater than 1, that means beta is RE1, so RE1 should be greater than 1 by GM. So effectively, RE1 should be less than R pi, RE1 should be less than R naught. So it should be less than both of them. So we will take minimum of the two, right? So RE1 should be greater than 1 by GM and less than minimum of R naught and R pi. Now we calculate these values for the reason, and we have these values with us. Okay, R pi is 4k, R naught is 100k, so minimum is 4k, and GM is 0.05. So your RE1 should be greater than 1 by 0.05 is 20, less than, and minimum of these two is 4k. Okay, so this one, right? See, let's move on to another question, that is to find the overall transconductance of the amplifier due to feedback. So can you give it a try? It's a simple question. I will draw the equivalent circuit. We will give it a try together. This is your V in R pi, RE1, GMBBE, R naught. This is from this node to this node. This is VF I naught. Okay, just follow this. Okay, correct me if I'm wrong, so that you will understand. So if I apply KCL at this node, what will be the KCL here? I naught will be equivalent to, let's call this node as V naught. Okay, and here it is RC. Okay, this is V naught. So I naught will be equivalent to, what is the current flowing from this node to this node? V naught minus Vf divided by R naught, right? Plus we have Gm VBE, correct? My I naught will be V naught minus Vf by R naught plus Gm. And what is VBE? Can you tell me what is VB? It is VB, it is E here. So what is VBE? VBE will it be V in minus VF, right? V in minus VF. Oh, right. So it will be V in minus VF. So I naught will be V naught by R naught minus VF by R naught plus GMV in minus GMVF. Now let me know what is V naught. If you look at here, look here, what is V naught? Current is flowing through here, it's I naught here. Current is flowing in this direction. So what will be V naught? This is RC. I naught RC, right? But will it be minus or plus? That's important. V naught, you are looking it from here. Oh, yes, right? It will be minus times I naught RC. And what will be VF? So if I naught current flows in this direction, so it has to leave as well, right? Let's, for the time being, ignore the base current. We can just directly write it as I naught because IB will be very less, so we can approximate this. So let's say I naught flows in this direction as well. So VF will be, to make our calculations easier, so it will be I naught times RE1, right? So let's just calculate now. So my I naught will be V naught, we calculated as minus times I naught RC by R naught. Similarly, it is minus VF. VF we calculate as I naught RE1 by R naught plus, then we have GMV in minus we have also GM that is again I naught times RE1. Now it's simple manipulation of the variables from here in LHS to RHS. Let's take I naught on LHS, I naught plus I naught RC by R naught plus I naught RE1 by I naught R naught plus GM RE1 I naught equivalent to GM V in. If I take I naught as common and R naught as LCM, so it will be R naught plus RC plus RE1 plus GM RE1 R naught. Let me just, here it will be on the denominator R naught, I am just cross multiplying it, so it will be GM times R naught into Vn. So can you tell me what is the formula for transconductance and what is transconductance? What is the transconductance? Simple conductance is current divided by voltage. It's the opposite of resistance. Resistance is voltage divided by current. So your conductance is current divided by voltage, but it is transconductance. So what will be the transconductance? It is output current by which voltage? Fill this. Do you know which voltage should I write here? Input voltage, right? So transconductance is output current by input voltage. So here we have input voltage, we have output current. So we can write I output by V input is equivalent to Gm R naught divided by R naught plus multiplied here on the denominator plus Rc plus Re1 plus Gm times Re1 R naught. Divide numerator and denominator by R naught, you will get Gm divided by 1 plus Rc by R naught plus Re1 by R naught plus Gm Re1. Now initially without feedback network your Gm was simply Gm. Now your Gm dash will be Gm divided by this component. It comes due to feedback. Okay. Is this understood? How we arrived at this formula? All the steps? Okay. Now again we have to find the input resistance. For these circuits, it's easier to find the input resistance and output resistance. We have to just find the feedback element, that is D1 plus A times beta, and only thing you should know is how to calculate it. Okay, that has been shown in the previous sessions, how you calculate the input resistance, output resistance of the amplifier. You apply, let's say, let me just give an example. If this is R pi, simple example here, this is GM VBE. Okay, so if I had to find R input, what I will do, I will attach a test source here, and we know we have the test source, we know the value, and we have the current IT that flows through it. Then how we will find the R in? That will be simply equivalent to VT by IT. You will apply a voltmeter, you will see what is the current flowing, then you know what voltage you have applied, you know what current you are seeing in the meter, ammeter and voltmeters. Then you will just use this formula, Ohm's law, VT by IT, you will get your input. So here as well, now from the circuit point of view, what it will give me, VT will be IT times R pi. Okay, so VT by IT will be R pi. So the value that you will see on the voltmeter and ammeter, and then you will use your pen and paper to calculate VT by IT, that will be equivalent to your R pi. That's how you calculate R pi using external elements. This is how you find the input resistance. And similarly at output, you will attach the test sources output, then you will see how you can calculate the output resistance. This has been shown, you can watch the videos, and here we will directly use the formula to calculate the input resistance and output resistance. And for this circuit we have this element, feedback elements for the negative feedback, that is 1 plus AB. They just first calculate what is this value. A is, we calculated A, that was GM was your 0.05, right? And beta is Re1, that's also seen. So it will be 0.05 into Re1, that was equivalent to 380. So it is equal to Wait a second. 380. 90%. So D is equal to 20, right? So D is 20. So your R in F will be final will be R in times 1 plus AB, that is D R in times D. So your R in for the circuit, as we saw, it was equal to R pi only. So your R pi we calculate as 4K into 20. So it is 20K. I will just go through quickly these few questions. Similarly, output resistance. Output resistance will be final will be output into D. R out is 100K into 20. R out is given to us. R out is given. Hmm, 1 second. I took the wrong value, I guess. Do we calculate R out? Yes. Yeah. R out is 100K. R out is R naught. So this comes out to be 2 mega ohm. Similarly, for gain, uh, you know that it will be AB final is equivalent to AB initial divided by 1 plus AB, right? So gain reduces. So here it is, if you have connected RC, so it is GMRC by 1 plus GMRE1. So it will be 0.05 into RC is 4K divided by 20, that is D simple. 200 by 20, that is 10. Okay, now let's just move on. Now I need you to answer the few questions. Okay, so now we want to obtain a low impedance and low input and low output impedance using the feedback amplifier. Which topology is mostly used? Can you tell me? So this is the question, you can look at the screen. What is the topology which will use to get low input and output impedance? First one, remember that the first element is sampling element and second one is mixing element, right? Okay, just current series. No, not current series. Because if you take current at the output, you will connect to the resistor in series. So that will increase the impedance. So you have to connect a resistor in parallel at output such that the resistance will decrease. So at output you will sample voltage, right? Such that your feedback mixer will get connected in parallel, right? So it will be a voltage at output, that is shunt at output. So you can Now you see, you now know it is voltage at output, so this one is gone, this one is gone. Now you have two options: voltage series, voltage shunt. Similarly, at the input you should connect your elements in parallel, so it is voltage shunt, right? So you connect it in shunt, you will get your both impedance will reduce. Okay, next question is in a series negative feedback amplifier, series you know. Now series at output means current at output and voltage at, mix the voltage at input. What will happen? In this I said just you are connecting these in series. So what will happen? Yes, correct. So both will increase. Okay, next is again I will just use the formula for these circuits. You have to calculate the input impedance. It is simply Rin divided by 1 plus AB, and the values are given to us as input impedance is 1K, output impedance 1K. You know how to solve these questions. I will just use the values. This is 100. Open loop gain is 100 into beta is 0.99. It comes out to be 10 ohm. Similarly, R out final is R out. It increases to 1 plus AB. It is 1K. 1 plus 100 into 0.99, 100K. And we have one more question related to this. Here also your A is 45, beta is 0.2, Rn is 1 kilo ohm, R out is 2 kilo ohm. So your RNF, you just need to know where the current impedance increase. You now know how you can know if the input impedance increase or decrease. Then you have to just apply the formula using D is 1 plus AB, right? You can just use the formula directly. You just need to know how impedance will behave. These are basic concepts. Let me just finish this and we have a few more and then we will end the session. Okay, so we're done with this. Okay, so I have one more question, a few more questions here. In comparison with the basic amplifier in a voltage series, select the proper option. This is a voltage series. Voltage at output and series, that means voltage at, mix the voltage at input. So if I take voltage at output, it is series or shunt connection. It is a shunt connection, right? Okay, voltage at input means series. So at output impedance decreases, at input impedance increases. So which is the correct option? Shunt output input impedance increases and output impedance decreases. So correct option is C, right? Okay, tell me about this. Which option gives the correct combination for input impedance? This is a voltage controlled current source. So at output, just remember that your answer lies in this question. It's a voltage controlled current source. So which option gives the correct combination for Z in, Z I? What should be your Z I and what should be your Z out? Think about it. Voltage controlled current source. You know, when you have a voltage controlled current source, okay, why Zdi should be infinity? Because such that if this is V in, this is your Zi. If this is Z in, let's say this is Zi. If Zi is infinity, whole voltage drops across this. Similarly, if this is your Z out and this is your ZL, and this should also be infinity, such that whole current will go through ZL, right? So that's why D option is correct. Nice. Okay, identify this now. What is the type of feedback topology? Give it 2 minutes and you will answer correctly. Current shunt. No. Current, if it was current, it would have been in series. Shunt, second part is correct. So your these options are out. Now you have two options. Shunt is correct. Now it samples voltage here, right? If it was in series, then it would have been current shunt. So now it's a voltage shunt, right? If I had a resistor here, so parallel, when at output it's connected in parallel, that means it is a voltage. For example, this is load and you connect your feedback here. You see this kind of image, right? This is connected in parallel, right? So it is a shunt. That is voltage. The sample is voltage, right? So last question, I guess. Okay, this one is the last. Identify the input impedance and output. This is of the ideal feedback network for current series amplifier. Current series amplifier. Current at output means series connection, and series at input means voltage connection, right? Guess. Now, if you are connecting your feedback network, D again. No, I guess you are wrong this time. You are talking about feedback network. You're not talking about. This is current here flowing. IX. And let me just completely draw here beta times Ix. So this is your R out B. This is your R in. Yes, this is R pi, and this will be here some voltage. So this is the connection, right? A. So your Z in B, that is R in B, should be equal to 0, right? And you are saying Z out B should also be equal to 0, correct? Right? For ideal case, it should be 0 and 0. If it was current mixing, then it was R out B, then it should have been infinity. But it is not the case. So R out should be Z out should be 0, and this should also be 0. So A is the correct option. Okay, so nice. You know these things very well. Good. So if you have any further questions, you can ask me because this is the last session for this course, and the course will be over and you will have exams, I guess, soon if you want to get the certificate. So if you have anything to say, because this will be the last time, this is the last session, this will be the last time I will be holding the session, and next will be next year, I guess, next session. So if you have anything you want to say, do you want to say anything or any general questions? Anything you want to say? Okay. So if we take next session, that would be from the August. The sessions will start again. Okay. Thank you for attending the session. I will just close the meeting now. Okay. Thank you. Best of luck for your course. Okay. Bye bye.